Introduction to Masonry materials. To determine the masonry assembly strength, we need to know more about the components of masonry. Masonry is really a collection of block, mortar, grout, and reinforcement. Masonry assembly strength is determined by the unit strength method, where we would need the block strength and mortar type, or the prism method, where we build a sample of block and mortar and do some testing. When specifying each material, we would need to know a block strength requirements, mortar type to be used within the wall, and then the corresponding grout strength and whether it's fine or coarse. For the blocks, we have concrete masonry units, which would be defined by ASTM C90. We could also have clay hollow structural brick units that would be defined by ASTM C652. Veneer, which would be non-structural, would be ASTM C216. Certainly the block is going to be the fundamental element of the masonry wall, both in aesthetics and in the strength of the wall. So the strength of the block is certainly a key component in understanding the overall strength. We have different types of blocks that you can see demonstrated here. Next, we want to look at mortar. Mortar is certainly the paste that's used to bind the blocks together. It becomes hard when it's set. It's made from a mixture of sand and cement or lime and water. It's definitely not as strong as the masonry units, and it really doesn't need to be. Its purpose is to be the glue between the units. So really a primary purpose of the mortar is going to be the constructability component of placing the mortar. The strength of the mortar tends not to be as important simply because the mortar ends up being in a very small confined bed within the masonry wall. So three different types of mortar that we have are M, S, and N. The overall strength of the mortar will go from right to left, with type N being the weakest, type M being the strongest in terms of the individual strength of the mortar. Well, that tends not to be as important of an issue. The overall assembly compressive strength, when defined by the unit strength method, both M and S mortar are going to really be the same thing. So as you move from right to left, really type N is going to be the weaker mortar, and then M and S are both going to be equivalent strength. So it tends to be not a reason to move from N all the way to type M. Type S tends to be the mortar that we would want to use for a structural wall. The other element to consider is again the workability or ease of construction, and that is an inverse relationship. As we would move from left to right, it would be easier to construct with the mortar. So it tends to be that type S is going to be the type of mortar that has the right structural properties and has the right ease of construction that makes it an ideal mortar for a structural wall. Grout is going to be an element certainly different than the mortar. It's essentially fluid concrete. Grout is going to be the material that we're going to use to bind reinforcement to the overall masonry units, right? So it's going to be that connector element between the two tensile element and reinforcement to the compressive element within the masonry block. So it has to fill the cores, it has to be able to fit into some confined spaces, which is where it is essential that is a very fluid concrete element. It's generally composed of a mixture of water, cement, sand, and pea gravel. Fine or coarse grout are both different options for grout. There's even self-consolidating grout, which makes it a very, very liquid applied element. So the difference between fine and coarse grout would just be the aggregate size that you would use. And the time to use fine grout would be whenever you would have some spaces that would have either a congestion of reinforcement, as you can see at the illustration at the bottom. And the last element within the masonry walls is going to be reinforcement. It certainly adds a lot of strength to the wall. It's going to be the element that's going to be within the wall that's going to have very good tensile properties. Concrete, whether it's concrete masonry units, grout, or mortar, all those different masonry elements that are concrete are very good in compression, but not so good in tension. So reinforcement is needed to increase the overall bending moment capacity of the wall. Here you can see a quick illustration. Within the bending of the wall, we have a lot of compression capacity, very little tensile capacity within the masonry elements. So when we add reinforcement, that's when we can balance out that compression and tension to develop a high overall moment capacity. Wall reinforcement within TMS 402 strength design provisions. You can see that there's some parameters for how to define reinforcement within the wall. Being less than a number 9 bar is important. Bar diameter to be less than 1/8 of the wall thickness, and bar area to be less than 4% of the overall cell area. So we certainly want to put some parameters on bar sizes as we're dealing within these confined spaces of masonry. Here I created a couple quick charts to help define what reinforcement should be used and what thickness of wall. You can see as we start to doubly reinforce masonry walls, we really do need to drop down the amount of reinforcement that we would be using in the walls. Which leads us to a couple quick examples I wanted to explore for an 8-inch masonry wall. When I have several different reinforcement options, different sizes, perhaps 1 bar versus 2 bars within a wall, what would a contractor prefer in both a 12-inch and 8-inch masonry scenario? Here with the survey results, you can see that with an 8-inch masonry wall, contractors tended to prefer the single bar within the wall spaced further apart. However, if I go to the 12-inch masonry wall, you can see that more options are considered equal. A very large bar spaced further apart is very similar to a smaller bar closer together, and the 2 bars within a 12-inch wall is suddenly an option that many more contractors would like to consider. One other thing to consider within this result is you can see the number 7 bars also could be one of the reasons why the contractors wouldn't prefer the large bar further apart. Within even a 12-inch wall, contractors would prefer to deal with number of 6 bars or smaller. So certainly bar size comes into play as contractors would be determining overall budgets for walls. So for the overall assembly of a masonry wall, when you're specifying it on drawings, don't just say what the overall strength of the masonry wall would be. Call out what each element would be: the CMU, the grout, and the mortar. For example, we could define a block strength to be 3250 or greater. We could define the mortar type to be type S. And once we know those two variables, we would know that our F'(M) should be 2500, which would then give us a grout strength of 2500 or greater. Again, coming up with the overall F'(M), we really need to just have the individual block strength and the mortar type defined, and then we can define what the F'(M) would be. These values can be found in the TMS 602, Table 2. Here you can see the 3250 psi block with the Type S mortar would give us the 2500 psi design strength. And then all the way down to 4500 psi for the block with Type S mortar giving us the 3000 psi. I highlight the middle row because I find that to be a very typical value that could be used throughout the country. And we've did a lot of research here at Forest to find out what the actual block strengths would be from the major block manufacturers in many of the different states. Here you can see a selection of the states and the different block values. You can see the average strength in the middle of the slide. The average strength for all of those different block companies would be 4400, which is far greater than the 3250 that I recommended on the previous slide. And then certainly if we ever wanted to go to a higher strength, you would have to increase all of the values, increase the block strength that you would be looking for, increase the grout strength to be whatever the overall F'(M) would be at the end. And then there would be a consideration perhaps to use Type M or Type S in that scenario. But either way, we're going to have to make sure that we have these elements tested with the prism strength method to make sure that we were able to achieve that 4000 psi for masonry. And then finally, why is F'(M) so important? Certainly it's going to make for a more efficient design for the wall, the bearing walls, even non-load bearing walls, certainly for shear walls. But a higher F'(m) also impacts the lintels that you use within the wall, giving a much more efficient lintel. Column and pilasters, lap links are a lot shorter. Connections to masonry. Then I'd also say that there is an accuracy component to this as well, as we tend to rely more and more on finite element analyses for our projects. Using accurate values is very important. And so making sure that you understand what the F'(m) is for your masonry wall would be very important in understanding what the overall analysis and results would be for that masonry wall. Lastly, at Force, what we tend to do is we try to make sure that we give enough documentation for everything that we recommend. These insights can be downloaded from our website. And that'll conclude the masonry materials video.